Our first speaker is Dr. Paul Ferkul. He's an employee of the University Space Research Association at NASA Glenn Research Center, and his topic is Fire on the Moon solid fuel combustion experiments as planned for the lunar lander. Now we'll start again. We're still ahead, so go ahead.
Slide. All right, so it's a quick science background, combustion at reduced gravity. For the last 40 years, NASA has recognized that studying combustion in reduced gravity is important for spacecraft fire safety and in exploration atmospheres, for fundamental science, and for applying the knowledge gained to terrestrial problems. The NASA Glenn Research Center has been at the forefront of microgravity research in combustion science and fluid physics from the outset. And in this presentation, I'm going to focus on solid fuel combustion as opposed to gaseous and liquid. So currently, NASA relies on a 1G test for screening material flammability for flight. You've heard some of these descriptions in Gary Ruff's presentation earlier today, if you happen to attend that. This test is a practical means to assess the great number of materials that need to be certified for example, the space shuttle or the space station or any future missions to space. However, microgravity research that we've done and others have done has suggested that some materials that will not burn in 1G will burn in 0G with a low speed flow. So this is significant. Or in partial gravity, such as lunar G. So if we do a 1G test that says, all right, this material is safe, well, our research shows that in some cases, it might actually burn in these reduced gravity environments. That's very significant. And the final bullet on the page represents normal gravity may not be the most flammable condition for a material. So it's very significant for fire safety and for fire fundamental research and interest. On the right is a image of two flames. This is from the space station. On the left is a concurrent flame, and these are both burning a fabric. So you see the direction of flow here. On the left, the flame spreads with the flow. On the right, the flame spreads against the flow. Again, these are done on the space station in the microgravity science glove box. So the significance here is this particular fabric on Earth will burn upward, which is equivalent to the figure on the left, but it will not burn downward, which is like the figure on the right. So in other words, on Earth, it burns concurrently, but not opposed. But in space, we just demonstrated, well, it burns in either direction. So this is kind of a quick presentation of how we expect some differences if we reduce gravity and then impose a lower flow, either through forced convection or a reduced buoyant flow. Again, Gary touched on this figure. It's a classic flammability boundary. It's a way to map where a particular material will or will not burn. It's typically done with putting some sort of velocity indicator on the x-axis, or it could be a g level. So we have a characteristic flow speed of the air, or we have a characteristic gravity level, which corresponds to a natural convective buoyant flow. On the y-axis, it could be a variety of things. In this case, we have % oxygen. And then we develop this boundary shown in blue. Within the boundary, the flame can exist, and outside the boundary, it cannot. So clearly, if you drop oxygen to a certain point, you see the flame cannot exist for any flow speeds. And if you increase the velocity too high, the flame cannot exist because it's blown off, just as you're familiar with blowing out a match on Earth. It turns out if you reduce the flow too low, the flame also goes out because there's insufficient flow of oxygen. So the critical thing here is looking at the hatched boundary, which is indicated by 1G studies. So you see this vertical line with the hatch marks. And we can only study this curve to the right of the boundary because of the inherent natural convective flows in any flame on Earth. We can never get flow speeds below that hatch boundary. So there's a large portion that we're trying to understand, both for fire safety reason in space and for fundamental understanding. If you get the next button, Gary. So again, a flow can be just strictly buoyancy or forced convection or a combination of the two. And to study the flammability boundary at low speed, we mostly have done tests in microgravity, but with an imposed forced convection. So now the lunar surface offers a unique environment of reduced gravity for a long duration to study flame spread at this non-Earth gravity level. Okay, so here the question is, and Gary showed us as well our centrifuge rig here on the left. It's a rotating chamber that we drop into a drop tower. We get 5.2 seconds. So we rotate it to generate a centrifugal acceleration, mimicking what we would expect in this case on the moon. So on the left is what a candle flame would look like on the moon. On the right, and the video is a little choppy, so it's not quite playing real time, but the idea is we can do tests right now to get some idea of how flames will look in lunar G, at least for 5 seconds that the drop tower has, and for fast responding systems. So there's significant differences between lunar G and 1G. We know this already. Also, quickly mentioned here that the lunar G flame on the left, you see it tilting to the left. That is the Coriolis acceleration acting on this rotating system. So that's an additional force or complication that we have to deal with rotating systems. So that will go away when we go to actual environment, of course, on the moon, because it will be a stationary system with a constant gravity level. Okay, so the proposed concept I'm going to discuss here, we're looking to build some hardware to do the first ever combustion tests on another world. So we're very excited about that. Again, the hypothesis, as I've alluded to, is that some materials burning in lunar G are more flammable than on Earth. This has important implications for the current 1G material screening method used by NASA. Right now, the concept is 4 fuel samples that'll be burned individually with cameras and other sensors to record the flame. Oxygen limits for upward and downward spread on the moon will be compared to 1G value, and also these 1G and lunar G results will be compared to detailed model predictions. These in turn will refine pressure gravity scaling relations and can be applied to other G levels, looking forward to like Martian G levels and others. And last here, the work directly addresses knowledge gaps in flammability and crew safety as defined in several NASA strategic documents. Here's a simplified schematic of the chamber. So right now we have a circular platform. This is looking down. We have internal gas bottles. You see cameras, 2 cameras. The fuel samples are kind of in the middle of the chamber. So this is schematically shown. There's a mixing fan, some sensors, and a heater, which may or may not be needed. Of course, the lunar environment temperature varies significantly, and it depends also on the particular vehicle and where we're located and so on when we get to do the test. So we'll have to figure that out in terms of whether we even need a heater, but I just indicate that here for completeness. Again, this is a schematic of what the engineering hardware will look like. We have the pieces and parts already in-house, and we're just literally going to start assembling here within a few days. You can see the samples located in the middle, flat samples and rods. They're basically thin sheets of fabric and small cylinders of plexiglass or PMMA. You see gas bottles and valves internal and other electronics. So the design allows for the height to be easily expanded. So with this, for 1G testing engineering hardware, we can increase the height of the chamber easily, leaving the floor the same. And also we will, because you might realize the cameras are pretty tight to the samples, we're going to have to utilize some sort of image processing algorithm to mitigate distortion from these cameras. So we have several modes of operation, as here, mode 1, mode 2, and mode 3. I won't go into too much detail. Mode 1, we want to try to keep the O2 in the chamber constant to get a good, what we call flammability test. For, whether a sample burns or not, you want to make sure the O2 is more or less constant. So the relative amounts of fuel burned compared to the volume need to be small enough for that to happen. So that was the first mode. The second mode, we would intentionally deplete oxygen. So we'd like ignite a PMMA rod and let it burn to extinction, which is when the chamber runs out of oxygen. Then we can record the oxygen and CO2, and then that will determine the limit. And the last mode is to look at planned normoxic environments. For example, some of these higher oxygens that Gary alluded to, where we know that things will burn much more aggressively. And we know also, obviously, that 34% on the moon could be quite challenging from the point of view of fire safety. So quickly, I won't go into this long. How big can a chamber be? It depends on how much fuel we burn. So we chose here a chamber volume of 10 liters we think is a good trade-off.
So 1 more minute.
Again, schematically, we're going to have all our stuff inside the chamber. The bulkhead will serve to put communication and power through to our experiment compared relative to the the lander, which will probably be a Eclipse variety, where we start getting unmanned missions to the moon initially. Concept of operations is very straightforward. During launch and transit, we envision the chamber would be essentially open. The valve would be open so that the chamber would be evacuated once it gets to the moon. And when we're ready to burn, we'd power up everything, close the chamber valve, and then release gases and fill. Once we reach our targeted environment, we initiate cameras and instruments and then ignite and record our flame. After the burn, we simply open the chamber valve to vent to the vacuum of the moon and then repeat the sequence for the next burn. All right, this is just sort of an overview. I won't go in, just for sake of time, you can just skip to the last chart here. And this is just a, a thought-provoking, hopefully, expression of humans and fire. Fire represents, for human's history, a significant change in our technology and what we could do. So, very roughly speaking, about 1.6 million years ago, early hominins harnessed fire from natural sources such as volcanoes or lightning strikes, based on evidence we have. Much later, about 300,000 to 400,000 years ago, basically fire became a controlled technology for hominin use, like, for example, periodic human cooking. So now the question, within 10 years, we plan to get humans back on the moon for extended durations at 1/6 Earth gravity. So how will we use fire there? So clearly, fire safety will always be a concern. But symbolically, I think it's important to consider, mankind spreading out to other worlds and actually harnessing this important technology in these locations. And then lastly, looking forward, within 100 years, will we have humans on Mars? That's yet again another gravity level to consider. And then, of course, other planets and moons. And these time estimates are, of course, just wild guesses based on what I would personally consider our challenges that we face. And the last two, of course, are wild speculation beyond our solar system. We know right now the nearest star is 80,000 years away to get there using today's technology. So is it a stretch to say that we will visit distant stars, planets within 1 million years? It's difficult to say when that will be, pending a breakthrough technology. But it's interesting that we're kind of in midpoint of when humans first use fire on this planet to when they might use them on a distant planet of another star. Thank you.
Okay, so while Gary gets set up for the next speaker, the chance for a question, if there's one. There's a two. One, why was PMMA picked for flammability, and about the flame temperature differences indicated by the colors of the flames?
Yeah, regarding the PMMA, we have a lot of experience burning that fuel. It turns out it burns nicely. We have a significant amount of data already that we've achieved on a space station. So that's why we picked it, because we know quite a bit and we can compare it to existing results. Regarding the colors, certainly the Lunar G flame is different than 1G. It is somewhat dimmer. It's not quite as hot, we think, because of the flow speeds are lower. And I think, regarding the insights into the implications of combustion products, I think there certainly will be some implication because of these lower residence times in the flame. We know already that soot formation can be, different in a high flow speed versus a low flow speed environment.
Okay, great. Well, thank you, Paul. This is it's great.